think of ourselves as molecular engineers, if you will. We build materials that are porous, so our entire research is focused on developing new porous materials for a variety of applications, but the particular kind of porous materials that we are focusing on are called metal organic frameworks, and we focus on these because they, like I mentioned, they're really molecularly tunable in that we can really mix and match. It's sort of like a kid in a Lego store. We can mix and match inorganic building blocks and organic building blocks, and we can really tune the properties that we want for a particular application. We're trying to impart a variety of functionality, just real-life functionality. For instance, we're trying to make to connect the building blocks such that they allow electron transport, for instance. Or we want to make the connections between the building blocks very stable so that we can use these materials in water, for instance. And so generally we're just looking to, I'm a synthetic chemist, so we're really looking to synthesize new materials, like I said, for a variety of applications. One of the really promising research efforts that we have is in the area of conductive porous materials. These porous materials that we work with, these metal organic frameworks, are attractive, first of all, because they have very, very high internal surface area. What that means is that you can think of it as having literally a sponge. And when you take the inside of the sponge and you lay it out flat, all that internal surface area, it'll be quite high, actually, even if you use a household sponge, for instance. But the sponges that we make and we design rationally have enormous surface areas. They have surface areas that can cover an entire football field. You take 1 gram of this material, and 1 gram is actually not a whole lot of stuff, right? And if you were able to we do a mental exercise, and if you're able to lay this internal surface area down flat, you would be able to cover with 1 gram an entire football field. So you can imagine now what the excitement would be if you could also make these sponges electrically conductive or ionically conductive. You would have this enormous surface area available for say analyte binding or gas binding or gas capture, but you would also be able to make it conductive. And the big question, one of the big questions in this field is, can you actually make these things conductive? This is where we come in. We make molecules and we think about the connections between the molecules such that they impart electronic conductivity or electric conductivity. And the potential applications for these are numerous. One would be that you can start thinking about electrocatalysis. Electrocatalysis is going to be huge in the future because it's related to many different renewable energy applications, for instance, CO2 reduction, O2 reduction in fuel cells. So I think a lot of people are interested already. We're just providing sort of a new age material for this kind of application. Another potential application for conductive, high surface area materials is in the area of batteries. If you could make sort of a solid electrolyte that lets lithium ions walk through and very fast, you would get a very high power density renewable battery. And so there's many different applications for these materials. The question is, can we make them? The answer is yes, because we were actually able to, we just had a couple of reports recently where we showed that these materials can be made. I mean, really people thought that the high surface area is incompatible with electric conductivity, and this is sort of intuitive because if you think about it, if you have a really good sponge, it's basically filled with air. How do you transport electricity through air? And it's not an obvious answer to that. But because these materials are tunable and we are actually able to engineer them at an atomic level, we can actually impart these new properties, and that's very exciting. Generally, in any sort of modern academic enterprise, you have to have collaborations. And especially when you're in the business of making new materials, me as a chemist, as a synthetic chemist, I don't have the expertise to perhaps make devices out of these materials. So we collaborate very strongly with colleagues in Japan. We collaborate with colleagues at the University of Osaka in Japan. We also collaborate with colleagues at MIT in the engineering school. You know, I am in the best place to do engineering, so I have to take advantage of that, and we do. So we collaborate with people in the research lab for electronics, and we are really making devices out of these materials. A lot of our ideas come from actually talking to industry people. They come in my office or they contact me through ILP mostly, and we talk about their needs. And we say, okay, we can help you, or my program is actually fit for helping you, or we have ideas that are already could be applied to your needs. Or if there's a particular interest that matches my group's interest, we go ahead and we form a partnership. That's one way to get ideas. Another great way to get ideas is actually, I would say, the old-fashioned way, which is talking to your colleagues, and I really have the best colleagues in the world at MIT, both in the chemistry department and in engineering. And by just talking to each other, you learn a lot from everyone, and you say, wait a minute, I have something that you could use. And they say, oh great, I'm glad that we met. So that's really mostly how we get our ideas. And I have to also mention that some of the ideas just come from the students. Again, I have the best students in the world at MIT, and some of them just come up with ideas that I probably would have never thought about.